Welcome back, Apologia, 8th grade Physical Science, Week 17, Day 3. Textbook pages 288 to 295, notebook pages 235 to 240. Experiment number 8.2, how fast you can work, will be done in class on February 7th. Technically, that was Week 17, Day 4. I just wanted you to know we will be doing that experiment in class. Okay, energy and work. Remember, energy is defined as the ability to do work. You may think it's work to read the textbook and answer the questions, but that is not the definition of work in science. In physics, work is a transfer of energy. You do work when you use a force to move something. The bigger the force, or the further you move an object, the more work you do. So the definition of work in physics is the product of a force applied in the direction of motion of an object and the distance the object moves. So work equals force times distance. To be clear, in science, work is only done when two conditions are met. First, an object must move. Second, a force must be acting on the object, either the whole force or part of the force, in the direction of motion. For example, remember in the last lesson we talked about the seagull. The seagull does work on the oyster when it lifts it up into the air. Work is done on the box in figure 8.21 by the man as he lifts it. Once he lifts the box and is holding it, the man is no longer doing work on the box. That may seem surprising because he is still exerting an effort to hold the box, but because the box is not moving, the man is not working. Even if he walks down the hall holding the box, he does no more work on the box because the direction of motion is not in the same direction as the force applied. Now, if he pushes the box along the floor, then he does work on the box because the force applied is in the same direction as the box is moving. If a force does not act in the direction an object is moving, it does no work on the object. All right, this is an important concept to keep in mind. Work depends on direction. All right, so let's really study this one. In step A, we have the direction of motion. So the box is going this way. The force is also going this way. So when force is applied in the direction of motion, the work done is maximized. All right, now B, part of pulling force in same direction of motion. So the motion is still going this way, but the force applied is going this way. So only part of the pulling force here, just this force, not this force. So only the horizontal part of the pulling force in situation B does work to move the box to the right. All right, now in C, the direction of motion is still this way, even though the force is going up. So because the lifting force C is not in the direction the box moves, no work is done on the box. Okay, now let's read this, a little bit about this. Okay. Notice in situation B of figure 8.22 that work can be done even if only a part of the force is acting in the direction of motion. It will be a smaller amount of work because the part of the force that is acting in the same direction as the box is moving is smaller than if you pushed the box, like in A. So although the box is moving, it's only part of the force is propelling it in that direction. Part of the force is going up. Since both the vertical part of the pulling part in B and all of the lifting force in C are not acting in the direction of motion, these forces do no work on the box. In science, work can also be defined as the change in energy of an object. Let's look at another example of work being done. All right, when the diver in figure 8.6 climbed the ladder, remember way back when, he did work. His muscles moved a force, his weight, up a certain distance, up to the top of the ladder. That is the definition of work. The diver gave himself potential energy. Potential energy is energy with the potential to do work. When the diver dives into the water, the energy changed from potential to kinetic energy. As the diver falls, gravity is now doing work on him, since it is supplying the force, his weight, and the direction of motion is down. Both the force of gravity and the direction of the diver's motion is down. So gravity does work on the diver as potential energy is changed to kinetic energy. All right, calculating work. We can calculate the amount of work, W, done by multiplying the force acting in the direction of motion by the distance that the object moves. The equation is shown below. So we have work equals force times distance. The units for work are the same as the units for energy. Notice that force units are newtons and distance units are meters. So work units are Newton meter, which is equal to a joule. All right, so let's go ahead and look at example 8.3. You lift a book from the floor to a bookshelf 1.5 meters above the ground. So D equals 1.5 meters. You exert a 19.6 Newton upward force in lifting the book. So your force is in the direction that the book is moving, which is 19.6 newtons. How much work did you do? So we're trying to solve for work, and that's going to be in joules. So step 1, write the list of knowns and unknowns. We've done that. Step 2, what equation are we going to use? Work equals force times distance. Step 3 and 4, write out the equation substituting the numbers from step 1 and solve. So force times distance equals 29.4 Newton meters, which is also equal to 29.4 joules. All right, power. Suppose you had to plow a large driveway after a snowstorm. Which of the ways would you want to use to remove snow? Would you want to use a snowblower, or would you want to just shovel it yourself? If you said snowblower, so you could get the work done faster, then you have an idea of what power is. In science, power, like work, has a specific meaning. Power is defined as the amount of work done each second. Or in other words, power is the rate of doing work. To do work at a faster rate requires more power. You can increase power in 2 ways. You can increase the amount of work done in a given time or decrease the time it takes to do a given amount of work. If you've ever shoveled snow, then you know moving snow from one place to another requires work. The person with the snowblower, however, can do the same amount of work much faster. Since the man with the snowblower can do more work in less time than the man shoveling, means the snowblower has more power. Notice that the source of the power for the man shoveling is the man himself, his muscles, and his energy. The source of power for the snowblower is the gas-powered engine. The gas in the engine supplies the chemical potential energy, which the energy converts to mechanical energy, enabling work to be done. Machines that have engines are often rated by how much power they provide. Think about a snowplow. The powerful engine of the truck pushing the snowplow allows it to remove more snow faster than the snowblower with much smaller engine. All right, let's figure out a way to calculate power. You can calculate power simply by dividing the amount done by the time needed to do the work. Again, because we said power was really the rate of doing work. All right, so the SI unit of power is the watt, which is equal to 1 joule per second, since work is measured in joules and time in seconds. The power unit was named after the Scottish scientist James Watt. You are probably most familiar with the watt when referring to light bulbs. A 65-watt light bulb burns 65 joules of energy every second. All right. Study 8.4 to see how to calculate power in an everyday situation. Then complete experiment 8.2 and on your own questions. Again, we are going to do experiment 8.2 next time. All right, example 8.4a. You lift a book from the floor to a bookshelf 1.8 meters above the floor using a force of 16.5 newtons. You lift the book in 2 seconds. How much power in watts did you use? All right, so it told us we used a force of 16.5 newtons, so we have that. It was 1.8 meters above the floor. It took us 2 seconds. How much power in watts? Step 2, write out the equation. Now, since we aren't given the value for work in the problem, we will have to use both equation 8.3 and 8.4 to solve this problem. So we have power equals work divided by time, and work equals force times distance. So if we combine the works, we can say power equals force times distance divided by time. So step 3 and 4, write out the equation substituting the numbers from step 1 and solve. Okay, so I have my force of 16.5 newtons times my distance and height divided by time, 2 seconds. So I get 16.5 times 1.8 divided by 2 equals 14.85 Newton meters per second, or 14.85 joules per second, which equals 14.85 watts. All right, 8.4b. A girl runs up a flight of stairs in 2.6 minutes. If the work she has done is equal to 320 joules, how much power did she use to climb the stairs? Okay, first of all, always write what we know. The work is 320 joules. The time is 2.6 minutes. Well, we should realize right there, we need this in seconds. So we can do a quick conversion. 2.6 minutes times 60 seconds over a minute gives you 156 seconds. All right, so now we have our seconds. We're trying to solve for power. All right, step 2, write out the equation. Power equals work over time. Step 3 and 4, write out the equation substituting the numbers from step 1 and solve. So we have 320 joules divided by 156 seconds, which equals 2.05 joules per second, or 2.05 watts. Your answer may have more decimal places. I rounded to the hundredths, but either way, you'll be fine. All right, so again, we're skipping experiment 8.2. We're going to do the on your owns. What conditions are required for a force to do work on an object? Some of the force must act in the same direction the object moves. On your own 8.9. A book is sitting on a table. The table is exerting an upward force on the book to support it as it rests on the table. Does this force do work? And explain. No. No work is being done by the table because the object that the force acts on, the book, is not moving. Remember, in order for work to occur, a force acting in the same direction of motion must move an object a distance. On your own, 8.19. All right. How much work in joules do you do when you use a 25 Newton force to lift a bag of potting soil from the floor to a shelf 1.5 meters high? If you lift the bag in 2 seconds, how much power in watts do you generate? Okay. Force 25 newtons, watts. Work in joules we're trying to determine. The distance was 1.5 meters off the floor. It took you 2 seconds. How much power did we use? All right. Step 2, what equation are you going to use? We're going to have to use them both. So we have power equals force times distance, that quantity divided by time. And then step 3 and 4, substitute the values from step 1 and solve. So we have 25 newtons times 1.5 meters, which is 37.5 joules divided by 2 seconds, which is 18.75 watts.